Hello, Professor Paul. This is Group 3, and this is our project on mitigating hallucination in security policy generation with LLMs, and this using a prompt ensembling approach. So, uh, our, we had help from Retrieval Maheswaran from RIT on the help for this project. So the background is that LLM can generate hallucinated or invalid outputs when creating XML policies. However, the challenge here is that single-step LLM prompting often has some limitations as it tends to hallucinate, or yes, tends to hallucinate, such as creating invalid values or text. Next, another issue is that there is a lack of structured training data, which prevents the creation of more advanced techniques such as knowledge graphs. Until such training data is being created, those advanced techniques, data-driven techniques, will not be possible. Lastly, there is no intent relevance filtering for single-step LLMs, so irrelevant intents might still pass through. So the goal of this project is to improve accuracy, reliability, and schema compliance in LLM-generated security policies. So our proposed solution is the prompt ensembling pipeline, which core idea is to decompose policy generation into specialized LLM prompt experts. This helps to reduce the cognitive workload on each LLM prompt, and which will help to reduce hallucinations. So the pipeline is as follows. It first reinstate the intent, and then the intent along with the reinstated intent gets passed into the 4 different experts. Then it gets passed through the schema checker, followed by the policy composer and the policy refiner, all of which are grounded by a schema representation table of the Yang data model. Another issue we identified is the intent relevance filtering. Because a single-step LLM assumes that any sort of intent might pass through, but in an actual practical situation, invalid intents might pass through, such as calculate payroll tax, or maybe some random mathematical calculations, such as 2 plus 2, which needs to be filtered off. So the solution to this is we can just add an additional LLM prompt as the intent relevance classifier as a pre-filter. This LLM prompt will just output whether is it a valid network security intent or not valid, means it's off domain in request. So we identified 2 failure modes. Firstly, the generated policies from irrelevant intents are syntactically invalid. These are less dangerous as they can be caught by the validator. Secondly, the generated policies from irrelevant intents are syntactically valid. These are much more dangerous because they are semantically irrelevant and they might affect the network although they are not intended to. So we did our own analysis on 2 different irrelevant intents. One of which showed that the intent is the generated policy is irrelevant, which is safe, as it can be called by a validator. Another one shows that the intent is synthetically valid, which is very dangerous. The one that is synthetically invalid is because it has a calculate action, which is not a supported action tag, while the others is all true because the action is invoke signaling, which is recognized action. So for our performance evaluation, we did 3 experiments. Firstly, we checked the syntactic correctness of generated policies. Secondly, we did a qualitative comparison of a representative intent. Thirdly, we did the accuracy analysis on the LLM-based intent relevance classifier that filters off domain inputs. For the first evaluation we did on syntactic correctness, we tested it on a dataset on 50 syntactic policy intents. On an average number of 3 runs, we found that the single-step baseline LLM did not generate any valid policies. While for the prompt ensembling approach with GPT-4o mini, we had a 52.6%. While For the problem sampling approach with GPT-5 mini, we had a stunning 86%. So this shows that problem sampling makes this possible compared to baseline single-step LLM approach. The next we did was performance evaluation, which we qualitatively compared the generated policies. So for the baseline LLM, it was invalid. It is schema invalid as it did not produce. It added a firewall node under condition. It added a firewall condition invalid tag underneath the condition tag, since firewall condition is not a recognized tag. Furthermore, it added an actions tag, but the extra S makes the tag invalid, while when you see our prompt sampling pipeline is valid throughout. Lastly, we check the evaluation of the LLM classifier for intent relevance filtering, and it does well as expected for 100 syntactic policy intents. GPT-4 mini gave a 91% accuracy, while GPT-5 mini gave an accuracy of 97%. So there's a bunch of trade-offs for this pipeline. Firstly, for the exchange for more prompts, it gave a higher accuracy, but as a result, it gave increase in latency. Furthermore, it's also schema dependent as it requires updates if the young data model ever changes. So to optimize this, some of the experts we can use smaller LLMs for these steps to optimize it, and we can create these smaller models by knowledge distillation. Furthermore, the young data model can be kept dynamic with changes when there is new young data model updates. So in conclusion, we contributed by the schema-grounded prompt assembling for I2NSF prompt policy generation, the LLM-based intent relevance filter, and the 2 datasets, and our open source code. Future directions could include building a Go dataset for intent to policy mapping, explore knowledge graph embedding models after these Go datasets are created, and functional testing with Open Daylight and Mininet to see whether our policies actually work behave as intended based on the intents. Okay, thank you. This is our source code.